it deposits, deposition, the gas deposits into a solid. You've all actually seen this. Do you have a freezer at home? Yes. Is there any frost in the freezer? Yeah, that was water vapor, that's a gas. And when it hit the very cold freezer door or whatever, it instantly turned to a solid. There was no liquid version. Frost on the bus window in the winter, it's just solid immediately, right? It's deposition. Ooh. Thank you so much. We're going to flip to the other page. Okay. Oh, that's all the notes that are going to be on it. Okay, so some students are like, Mr. Boder, why did you have us draw it if it's printed right here? I wanted you to draw it one time. No, I don't need you to draw it again, but we do have to refer to it. Here's your solid. Here's your liquid phase. Here's your gas phase. Let's take a look at this graph. Oh boy. This graph is going to be the hardest part of the lecture because it's the part that I'm actually going to test you on. Reading these graphs is like a crucial skill that you need to be able to do for the test. Let's take a look at what the graph is showing you, and then we'll talk about it. First up, I need to tell you what this is a graph of. This is the phase change graph, of a single pure substance. I needed to tell you that this is the phase change graph of a single pure substance for a reason. It will allow us to interpret what the graph is showing. It's the phase change graph of a single pure substance. Make sure you label it like that. Let's take a look at the graph. As you go up the y-axis, what is increasing? So as you get higher here, the temperature is hotter. As you go this way, we see time is increasing. We're going to add a note onto that. Not only is time increasing, but also we're adding heat is added. And then, in fact, we're going to add heat at a constant, steady rate to this sample. We've got a little sample of stuff, and we're going to add heat constantly as we go this way, and then we're going to track and watch what the temperature does as we add heat at a constant rate. We're going to start with a solid. Down here, we're going to start with a solid. Now, don't overthink this one. You've got a solid. As you add heat, what's going to happen to the temperature? Yeah, so here we've got a solid heating up as we go that way. A solid is going to be heating up from point A to point B is a solid heating up. That makes sense. Wait, what is heat again? It's random particle vibration, right? Random particle vibration. Heat is random particle vibration. What's temperature? The average vibration, though, right? Okay, so as we add more heat, it would make sense that the average vibration would increase. So the temperature should increase, yeah? That happens for a point, for a while, but then we reach a point where something weird starts to happen. We're adding more particle vibration in, but the average speed doesn't increase. It gets stuck for a while. Even though we're adding heat in, the temperature doesn't change. What the heck is happening there? That's the melting point. Watch where I draw this little whoop-de-doo. That's melting. Okay, we'll get there. That's melting. So you're wondering, well, Mr. Boder, you're adding heat, so you're making the particles vibrate faster. Shouldn't the average speed continue to rise if they're vibrating faster? It doesn't, and I'm going to talk to you about why. Let's look at the particles. In a solid, you've got the particles, right? They're all vibrating, but there are bonds between them. They're attracted to each other. They like being there. When I make them vibrate faster and faster, eventually I'm going to break those bonds and they'll be able to rotate around each other and flow. But it took energy to actually break that bond. It was not free. They wanted to be there, and I had to be like, and break them free. And then they could flow. Oh. So while I'm adding heat, and the temperature is not increasing, where's that energy going? What's it getting used to do? It's got to break those bonds apart. And so the average speed, if we measure the average speed of the whole sample, doesn't change. The orientation of the particles to each other is changing. They're going from that solid locked in to free. And so you have some that are free and can vibrate around, but you still have other ones that are locked together. And if you average the temperature of that, you average the vibration speed, it stays at 30, or it stays at whatever the freezing point is, until they're all totally free in the liquid form. That is called the heat of fusion. The heat of fusion is the energy associated with, and it goes either way, either forming those bonds or breaking I gotta be more specific. The heat of fusion is the energy associated with forming or breaking the, ready for this, intermolecular bonds of a solid. The heat of fusion, it's also called the latent heat of fusion, is the energy associated with forming or breaking the intermolecular bonds of a solid. The particular level of that energy, like the amount it takes, is unique to every substance. Water has a pretty high latent heat of fusion and a really high latent heat of vaporization. Other substances, like carbon dioxide, have a very low latent heat of fusion. They will very happily break apart from each other. But it does take energy, just not very much. That's the energy that it takes to break those molecules apart. At this moment, from B to C, oh, sorry, I'll back up. From A to B, we had a solid heating up, right? During B to C, what is present there? Do we have a solid, do we have a liquid, or do we have both?
Both.
Yeah, so we'll have a solid slash liquid. This is your ice cube. As it's melting, it's got melting water flowing over it. There's both solid parts and liquid parts. What will the temperature be while it's going through its melting phase? 32 Fahrenheit or 0 Celsius if it's water. The whole sample itself will be stuck at that temperature. All the energy that you're putting into it is going into breaking those bonds apart from each other. Okay? Again, I'm going to warn you, this is a difficult concept. Talking through this whole graph is something that you're going to need to be able to do. Woo! Okay. We melt it, melt it, melt it, melt it. Boom, at point C we have all of the particles have been melted from each other and now they can flow freely. So now we have a liquid, and again we are finally now able to heat it up. Heat it. So now we have a liquid that's heating up as we go up. The temperature can continue to rise. At a certain point that temperature can go no further for that liquid. Why? What begins to happen for that liquid? Yeah, we're heating it up, so we're going to get it to the boiling point. And again, watch how I draw this. Boom, here we go. Now we're boiling. We've risen the temperature of the liquid. It's getting warmer and warmer and warmer. And then, boom, it hits a point where it boils. While it's boiling, can the temperature of the substance rise?
No.
Why? What's the energy doing?
Breaking even more of them.
Yeah, we have these, the liquid is able to flow on itself, but the molecules are still attracted to each other. They're still little magnets to each other, and it takes some energy to break them free. As they're a liquid, they're flowing, 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 and I get them vibrating faster and faster and faster, and then at some point they're vibrating so fast, can they stay together? No, they'll break free. But as they break free, they take with them a tremendous amount of energy,